for the intro. Also, super excited to be here. We have a pretty small group, so I'm hoping if you have any questions, either put them in the chat or raise your hand, or even feel free to interrupt me since we have a pretty tight group. Let me share my screen. So today can you see my tab? Yeah, you can see my presentation?
Yeah.
Perfect. So today I want to talk about pipeline engines. Maybe a quick intro for myself. So who am I? So first thing I'm going to tell you is that I'm actually not a bioinformatician. However, I would consider myself an expert in building software. I've been building software for about 20 years. And previously, I co-founded a company called Dooly, and I was the CTO there for 7 years. We went on to raise a lot of VC funding, and we grew that company to 50 plus people. Why am I here? Great question. The reason is because I'm now working on a tech bio company, and that company is called Beaker. And I'm actually building that with my co-founder and partner, Forum, who's on the call as well. She's the hardcore scientist. I'm more the software engineer. So I'm hoping with this talk to give sort of a little bit more of a software angle to sort of pipelines and bioinformatics work. And I hope that that can be insightful, because I think that often maybe some of those points aren't covered as thoroughly. I can't actually see the chat, so maybe Yasmin, if anything comes up, if you could just let me know, be great. So agenda, we're going to look at 3 different things. We're going to look at pipelines in the wild, properties of pipelines, and then just quickly talk about Beaker. And we're going to just dive a little bit deeper into containers and cloud deployment, specifically because those are areas where I have a decent amount of expertise. What is a pipeline? So we'll start with the basics. You already probably know this, but I think reminders are always good, especially for complex topics. So a pipeline, this is the definition from the dictionary, a channel by which information is transmitted sequentially. The first information in is the first information out. So this is specifically like a computational definition of a pipeline. Pipelines are everywhere. We use them in bioinformatics, but we also use them in all sorts of other applications. App automation. So if anyone here actually uses an iPhone or uses a Mac, Apple actually ships with these 2 apps. The first one is called Automator. The other is called Shortcuts, to build pipelines to automate things on your computer. So if you look at Shortcuts, you can see each of these boxes are steps that take inputs and then feed outputs that you can put into the following steps. So very similar to what we do in bioinformatics in a lot of ways. If you are a developer, or even in bioinformatics, you probably possibly have done some continuous integration, continuous deployment. So as developers here, 2 products, Circle CI, GitHub Actions. When we push code changes, we run pipelines to test our code and also to automatically deploy our code. So these are 2 separate products that do that. Here are other examples. So software as a service automation. So on the left, we have Zapier. On the right, if this, then that. And these are 2 examples of web tools that can string together all of your different sort of software as a service apps. For example, when you like a song on YouTube, this integration can automatically add it to Spotify playlist. Marketing automation. When you receive emails in your inbox, newsletters, surveys, etc. Often those things are cobbled together using marketing automation software. And this is just software that sort of basically you build these sort of workflows, and based on the user's journey, where they are in a journey, for example, if they've seen a page, if they've responded to an email, you can sort of send them along these different paths. So also very common. One thing that's interesting too is that your tools support pipelines too. And just a reminder once again, because I think often we forget this. We're familiar with Bash or Zesh or different sort of command lines. This is a pipeline in Bash, right? So this pipeline has 4 steps. These are 4 different processes that are going to be executed. These are called pipes. So pipes take the results, the output from each step, standard out, what we call standard out, and sends it to the next step. One cool thing with pipes in Bash as well is that it will actually stream data too. So standard out will be streamed to the next step. We don't need to fully execute and finish this process before. I'm assuming you can see my mouse. Can you see my mouse?
Yeah.
Okay, perfect. So we don't need to wait for this to finish completely before sending it to sort. So one of the properties of pipelines that make them a bit more efficient is this property of being able to stream results between steps. Just going through this pipeline quickly. So the first step takes input. Here's what my input looks like. We pass that to the TR command. The TR command allows us to split that input into new lines. So in this case, we are splitting every word from that input onto a separate line. Sort is now, we'll receive that input with every word on a new line. We'll sort them so that basically these are alphabetically ordered, and so that the same words will appear adjacent to each other. Pass that to unique to remove any adjacent lines. And then we can count those words, throw that in output, and now we have a pipeline that essentially takes a paragraph of text and counts the number of unique words. If you've ever compiled software, maybe you've used the make, maybe you have typed make on the command line. Make is actually sort of a pipeline tool under the hood. So what make does is you define a bunch of different steps, and then your steps produce an output file. So the first sort of string here before this colon character in each of these steps is the file that's going to be produced. And then after the colon, we have the dependencies, what's required for this step to run. So in this case, when I run make, it's going to try to generate output.text. Make will look to see what the dependencies are. The dependencies here are step3.text. If that doesn't exist, it will execute the step3.text step or rule, and then it'll sort of do that recursively. So it'll actually start at the first one here to get to our output. What's interesting with tools like make as well is you actually, each of these intermediate steps, the results are cached, and because we're outputting the results to these text files. So for example, if I change my last step here to maybe I want to count something else, I want to count I don't know, I want to count how many characters are in the string. I change this. Because step3.text already exists, it actually will not rerun all of this. It will only rerun this step. So this is a feature very similar to what we see in sort of bioinformatics pipeline engines like Nextflow or SnakeMake or other ones that can cache intermediate results. Lastly, I just want to show also that a lot of programming languages support pipelines too. So this is a proposal for a pipeline operator in JavaScript. You might not be familiar with pipelines. This is not actually in the language yet, but you can sort of use plugins to enable this. And this is just a way to take output of a function and kind of give you cleaner syntax to pass it to subsequent expressions. Any questions about any of that stuff so far? Fairly straightforward. Got a thumbs up. Perfect. Let's switch gears a bit and talk about bioinformatics pipelines. I want to talk a bit about properties of scientific pipeline engines. This is actually from SnakeMake, has a paper. I've added the source below, but essentially, they kind of bucket what's important in scientific pipeline engines to sort of three different categories. The first is these engines should help us to produce reproducible pipelines or reproducible code. The second is they should be adaptable. So we should be able to reuse components of them in other pipelines, in other work, so that we're not constantly reinventing the wheel. Also, we should be able to extend existing pipelines easily. They should be transparent. One of the big problems that we've seen in sort of our research, and I'll get to what we're building later, is that there's a lot of data out there where people don't actually know how they were produced. There's no metadata, as I'm sure you've all encountered this. And as I'm sure you've also all encountered sort of like tools that don't install these sorts of things. So these are some of the problems that we're trying to solve with scientific pipeline engines. In terms of reproducibility, we know that dependency management is one of the big challenges. We can't run pipelines without installing the necessary software dependencies, libraries, interpreters, code, binaries, etc. And this is really a problem because, as you know, dependencies are always changing and execution environments really differ. So there's two ways really that pipeline engines solve this. One of the ways is that they have built-in support for package managers. So if you've used the pipeline engine like Nextflow, you've seen that you can specify a list of conda dependencies. So Nextflow will actually run conda, get those dependencies, make sure that your operating system is configured with the right version of Python or R or whatnot in the right libraries, so that the pipeline can run in a reproducible way and you don't need to worry about installing all of those dependencies. There's another way that we can sort of manage dependencies, and that's containers. So containers are a bit different because they actually fully encapsulate a pipeline dependencies and can be shipped to sort of any execution environment. I'll talk a bit more about this because this is an area where I think I can provide a bit more value coming from more of a software background. But containers are really important because containers ensure reproducibility. Package managers don't always ensure that. Here's a graph from a paper I think published by some of the Nextflow authors, but you can see here that they've demonstrated that if you solely depend on installing packages using a package manager, they ran a pipeline on Linux and they ran a pipeline on Mac OS. And what you can see is actually some of the results differed between the two, which is obviously not good. With containers, the results were the same. And the reason for that is because package managers can make sure that sort of the high-level dependencies are the same, but where they are often a little bit more brittle is some of the sub-dependencies. For example, maybe Python on Mac OS relies on a certain version of a little bit of a bad example, but a certain version of OpenSSL that ships with Mac OS. And then on Linux, on Linux, there's a different flavor of OpenSSL that ships. The package manager won't go deep enough to sort of manage those dependencies in a lot of cases. It will stay at sort of like the library interpreter level, but those underlying packages could work differently in very subtle ways. So let's talk about containers. So you might be, I'm sure you've probably are a little bit familiar with both of these. So we have sort of, there are two different sort of machines, which you've probably heard of, have probably used. The idea behind a virtual machine is that you have an entire sort of fresh operating system with the kernel running in an isolated environment. The virtual machine is not aware, the software running is not aware that it's running inside of a VM. And obviously, we run this often on cloud infrastructure, Amazon EC2, etc. This is obviously very heavy because each of these virtual machines take a ton of resources and are shared. Each virtual machine shares kind of the host resources. What's interesting with containers, and this I want to talk just a little bit more about because I think a lot of people really don't fully understand how this works. What's interesting with containers, you might start off a container, you might write something like a Docker file, you might say, hey, this Docker file starts off from Ubuntu. Ubuntu is a Linux distribution. That doesn't mean that the container is actually running Ubuntu. What that means is that the container has access to all of the sort of programs that Ubuntu ships with. Some of the programs that Ubuntu ships with, for example, you have all the regular stuff like Bash, right? Our shell is a program that ships. It's literally just a program that we execute. And you maybe it ships with wget, a package manager like app to apt, and all these different things. However, a container doesn't ship with the kernel. So even though our container, we say, hey, this is coming from Ubuntu, we don't get the Ubuntu kernel. We only get the user space, binaries, and libraries. When we run a program in a container, or for example, if we run, say the Bash program that ships with Ubuntu, the way containers work is they will intercept system calls. So the way that programs interface with the operating system in almost all operating systems is there is a list of calls that programs can do to the operating system. One of those calls, for example, could be, hey, create a new process, because processes are a feature of the kernel of the operating system. Another one could be, hey, I want to create some shared memory that multiple programs can access. That's a feature of the operating system. So the operating system itself, the kernel, gives us an interface, sort of like a library that our user space programs can use. What containers do is they intercept those system calls and translate them to the host operating system. So for example, if I'm running Bash inside of a container and I run ls to list files, by the way, ls is just the program like any other program, then ls will make a system call. It'll talk to the kernel. It will make a system call to get all the files in whichever folder you're in. Docker, or the container engine you're using, will intercept that system call and basically translate it to the host operating system. And often we can define sort of that translation layer in like our Docker config. We mount volumes, different things, and then the host operating system will come back, give it to Docker, that will then massage it and give it back to our container. So that's the primary difference with containers versus virtual machines, whereas virtual machines, the entire kernel is running and everything is sort of, I hate to use the word emulated, but let's call it emulated down to the processor level, whereas with containers, it's all running on the host operating system. Any questions about that?
I actually have a question, Justin. So, in which cases you recommend to use a virtual machine? Like, can you make a case for that? And in which case do you recommend to use a container?
Yeah, for sure. So cases where you might use virtual machines, um, I would say so if we're, for example, when we're building software, sometimes we have things we want to deploy on Amazon EC2, and maybe we just want a box, for example, where we can just install our tools, run a server, install some tools to make sure it's always running. And we just want to be able to SSH in. It can be like an easier developer experience if we have something that we know is static, persistent, kind of needs like a dedicated amount of resources. Sometimes having that sort of flexibility can be a little bit easier. If you are using containers, sometimes sort of like the developer experience can be a little bit more difficult. For example, if you have a container and you deploy that thing somewhere, good luck sort of like SSHing in, making some configuration changes,
Mm.
etc. You're going to need to change like the container image. Although you can run an SSH server in a container, you can do all those things, but those changes won't be as persistent. What I would say containers are great for. Containers are great for reproducibility. Really, if you have something that you need multiple people to run, or you need to run it on multiple clouds, or you need to run a lot of them. One thing with a virtual machine is you're not going to be able to spin up 100 different virtual machines and then writing code to sort of automate running these tasks and deploying these tasks to all 100 of them is going to be really difficult. You're going to burn your wallet really quickly as well, because those are like full, full machines with a ton of memory and like a lot of compute allocated to them. Whereas with containers, you can say, hey, I want to run 100 instances of this container. They're each going to take 5 minutes, and then they're going to shut down. So we only sort of need to pay for how much compute and memory, well, how much time we've used really for each of those. So I would say they're a lot more nimble in that way. And there are also, for example, cloud services that allow you to sort of deploy containers on demand, run a task, and then shut them down. So it can be really easy, just for kind of like scaling workloads, making sure it runs everywhere, making sure they're nimble and they don't burn a hole in your wallet. I don't know if that sort of answers your question.
Yeah,
It's like one's
definitely.
really beefy. One's like having a, you know, one's really super beefy. The other is great for scaling the number of workloads. And like if you need to ship this thing to a lot of different places, but can be a bit harder to set up, I would say.
I see. Yeah, as a bioinformatician, we use containers all the time, but virtual machine, it's probably, I don't know how can fit in bioinformatics, in which way, maybe when you need to test a software, just like what's your experience?
Yeah, I mean, like so in software development, when we are building web applications, these sorts of things, nowadays it's very common to use containers for everything.
Mhm.
And part of the reasons for that are, like I mentioned, it makes scaling super easy, right? I could be like, hey, I need another instance of this database because there's so much traffic. Boom, just ship another container. And multiple containers can sometimes run on the same nodes, on the same VM, these sorts of things. So nowadays, I would say the trend is to use really containers for everything. But I think there is definitely a use case, especially in bioinformatics, where, hey, maybe you're developing a pipeline and you need to run that, you need to develop this in the cloud because you don't have enough uh, compute or memory on your local computer. So spinning up a virtual machine to do that development can be a lot easier than like trying to change your Docker file, pushing that Docker file, waiting for the results. Like that's
Mhm.
a very slow and tedious sort of like feedback cycle. But containers are more flexible in the end for like production software, I would say.
Okay, thank you.
Yeah, you're welcome. And just guarantee that reproducibility as well. Allow other people to pick it up and just run it. Pipelines, we know that pipelines need to be able to run in different environments. Super important for reproducibility as well as just scaling, right? Like we just talked about, you might start on your personal computer and then you find you need to deploy this thing to your cluster or to the cloud. So pipeline engines help us with that as well. And part of the way they help us with that is they abstract the underlying execution environment. So for example, a pipeline engine, you will define sort of, hey, here are the input files, here are the output files. And then in its configuration, you will say, actually, I need this to run locally, or I need this to run on AWS or Google Cloud, or these different environments. I want to talk a little bit about how some of these cloud setups work. Because I think there is still a lot of people who are used to running sort of these pipelines locally or on clusters where you sort of like get your own shell and it kind of feels like you're developing these things locally. Whereas if you are pushing these things to the cloud, sometimes the paradigms can be a little bit different. So I'll touch on sort of two models here for running these things on AWS. One of these is AWS Batch. So AWS Batch is a product run and maintained by Amazon. It's part of the Amazon Web Services family. This graph looks really scary. Don't worry, I'm gonna try to break it down. It's not too frightening once we build a general mental model of how this works. So the idea behind AWS Batch is that you are able to submit jobs to it. And then what AWS Batch does is it actually takes care of spinning up VMs for you behind the scenes. And those VMs run Docker. And based on if you submit 10 jobs, it will take care of running those jobs on sort of those EC2 instances. An EC2 instance in Amazon Web Services world means a VM in the cloud. So it will actually take care of taking your job, spinning up an EC2 instance on demand. Some of those instances will be able to run multiple tasks at the same time. It will take care of submitting that task, that job to the EC2 instance, running it, and then giving you the results back. Once the queue is empty, there is no more work to perform. It will actually spin these instances down automatically for you. So this just makes sure that we're not wasting compute. We don't have these instances in the cloud that are up and doing basically nothing. And the other thing this gives us is it also gives us the ability to sort of like parallelize our workflows in a more efficient way. If we submit 100 different jobs, we're able to configure this to automatically spin up a ton of these VMs that are running Docker to be able to run that efficiently and really fast. And what's really nice with something like AWS Batch is, again, we don't need to worry about these underlying VMs. AWS manages that for us and only allocates what we need. And you can also do things like configure sort of, hey, this job will require a machine, will need to run on a machine with this much memory and this many virtual CPUs and things like that. The way you would, and what's cool with sort of pipeline engines, again, I'm going to use Nextflow as an example, is you can just swap out the connector, the executor, because Nextflow is designed in a way to be obviously execution environment agnostic. So you're able to say, hey, I want to run this workflow in AWS Batch. And once you've done some initial configuration, it will go and use this whole process for you. And so that your workflow is portable across a lot of different execution environments. So this is a really great choice for doing this. Any questions about this? Something else you may have heard of in terms of cloud infrastructure is Kubernetes. This is something I have a lot of experience with as well. So I figured I would touch on this too, just to sort of give you a high level take of what Kubernetes is. So we know that to run Docker containers, we need an operating system. And so what Kubernetes is, Kubernetes allows you to sort of define a bunch of virtual machines that all run Kubernetes, and then Kubernetes has an abstraction where you can submit jobs or different things to run, and Kubernetes itself figures out where it should run the container. So if you have a container and you say, hey, this container actually needs, it needs a ton of memory, Kubernetes is running on a few what's called worker nodes. Those would be like the different sort of systems or virtual machines. Kubernetes will look at, okay, which of these worker nodes can actually support this container based on its memory and compute requirements, and will schedule that job onto the right worker node for you transparently. So that's like the idea behind Kubernetes. It's used a lot. It's actually a project that was started by Google, I believe, and it's used a lot for sort of companies that are building infrastructure where IT teams are like maintaining this like Kubernetes cluster, and all these different people can just schedule containers, and Kubernetes takes care of running the container, making sure it stays up. If there's a problem with the worker node, it will reschedule the container onto a different node, etc. So how do we use this in bioinformatics? Again, using Nextflow as an example here. We use the Nextflow Kubernetes driver. We submit a job, and then Nextflow will take care of submitting that job to Kubernetes. Kubernetes will schedule that onto a worker node that can support it, and then we'll get the results back. One thing I will say about something like Kubernetes, it is a lot more difficult to sort of maintain and run than something like AWS Batch. I would recommend, like, for most use cases, unless like you have like a really large IT team and you want to do a lot more advanced things, I would definitely recommend looking into a service like AWS Batch that kind of like transparently handles a lot of these things for you, a lot of the configuration and spinning up of things. Whereas with something like Kubernetes, typically you will have like a fixed set of nodes in the background. So they're used in like much larger companies that have like very specific compute requirements and different things. Storage, portability, right? So pipeline engines also help us abstract storage providers, whether it's local disk, S3, Google Cloud Storage, etc. One other thing that's really important with pipeline engines too is that they can take our workflows and they can break them down so that multiple tasks can execute in parallel. So for example, if you're running Nextflow and AWS Batch, if you have a task in a workflow that can be parallelized, Nextflow will make sure to sort of like spin those up in parallel as separate AWS Batch jobs that can then be scheduled onto separate VMs. Sometimes data between tasks can also be streamed. So for example, if you have a compressed FASTQ file, as that FASTQ is being decompressed, you can actually pipe it into, you could stream it into something like FastQC. So some pipeline engines will actually support this. However, if you're doing that, you really need to be careful about what executor you're using, because if, for example, those things are running on two separate boxes, that data isn't going to be able to be streamed. Typically, that means the executor will have to schedule those onto the same box so that the in-memory results can be accessed by both processes. Well, I think something that's really interesting too is there are so many, right, pipeline engines, different takes, different attempts and whatnot, but really different trade-offs, I would say, between flavors of pipeline engines. So here's a bunch of different ones. There are sort of 4 broad categories that were actually defined in the next flow paper, referenced in a few slides back. One of them is GUI based. So for example, Galaxy, generic programming language based, domain specific language based, and configuration based. So just to show you sort of like examples of those. So GUI based, right? Galaxy, you could sort of string together your nodes in sort of a graphical user interface, but it's really becomes a lot more difficult to do more complex things where you may need access to the underlying code. So this is great for sort of stringing together common tasks, but can start to break down if you need a little bit more flexibility. And those are kind of some of the trade-offs, right? We also have a lot of pipeline engines that are generic programming language based. So here's one called Hyperloom. And the way Hyperloom works is you import the Hyperloom library into sort of your script, and then you call functions from that library to do things like submit task. So the abstraction is very low level here. The abstraction is essentially a library that you import. And there are advantages to this. It can maybe feel a bit more powerful because you're essentially just writing a script, but there's also a lot of disadvantages. Now you're kind of stuck having to write each of your scripts from the ground up, and sort of use this library to figure out how to cobble together these jobs. So they don't make the job of stringing together these pipelines like super easy for you. And then we have ones that are domain specific language based, like SnakeMake. Again, this is from their paper, but here you can see that what a domain specific language is basically that there are identifiers in the code that relate directly to the technology. So in this case, we have some of those identifiers here will be rule. So rule is a SnakeMake specific thing that tells us this is a step in the pipeline. And same thing with, for example, output log. So essentially what this is trying to construct sort of like a language, if you will, like a little bit like syntax around pipeline functionality, so that you don't need to say, hey, import this library, connect to this server, submit this task. Here we're just saying, here's the rule, here's the rule, here's the rule. And hopefully this is a little bit more readable and easier to parse, at the sort of expense that, hey, you need to learn what these rules are, and you need to learn how this works. Like, when is the select by country going to be executed? So those are kind of some of the trade-offs. Of course, I would say like this isn't necessarily the hardest thing to learn. And once you do learn it, it becomes like, I think, a little bit more intuitive and easy to work with. And finally, we have sort of some pipeline engines that are configuration based. So in this case, your input to the pipeline engine could be something like a large blob of JSON, where you say, here's a JSON array. Okay, here are the steps. Step one is container. Here's pass the container in, pass the arguments. Okay, step two is container again with these arguments. And in that case, some people like this, but it really, in this case, you don't have access to sort of like, you can't write your workflows using just like a programming language. You're really using like defining this using configuration or like some sort of data structure. So it ends up being a lot more limiting, but can also maybe be a little bit easier to use in some cases because you're more confined in terms of what you can or can't do. Traceability and documentation. Pipeline engines obviously can generate some reports for us. I'm just going to share a different tab here. So here's an example report from SnakeMake. One of the issues we've identified talking to sort of doing a lot of market research on the product we're building is just output files and artifacts where people don't know how they were produced. what were the input files used, what steps were performed. Pipeline engines can help us with this as well. Some of the ways that they can help help us with that is they can generate reports. So, for example, here is we've run a pipeline, and this is a report that was generated. And from here, we can see all the different rules. If we click into these rules, we can see, hey, here was actually the input file to this. Here's the output. Here's the software that was used, including the version number for this rule. And I think really cool, like here's the code for this specific step. And I'll actually go, for example, this is a bit more complicated example. So this is actually amazing for sort of like sharing, hey, what's the work that I've done on this thing? And pipelines are really useful for that. If you're using pipelines for development, you could sort of like share this with other people or even store it with your output files. And then when you move on to a different project or someone moves on, other people pick this up, can know exactly what happened. So a really nice bonus of working with.
Live streaming is on.
Perfect. So yeah, really great for audit logs, etc. And finally, in terms of helping us with being adaptable, pipeline engines are great for composability, especially if they can help us extend existing workflows, but also share steps. There are, as you're probably aware, huge communities of different sort of open source pipelines, as well as components of pipelines out there. So whether that's NF Core, if you haven't checked it out, definitely recommend it, as well as other ones like DocStore, where people publish pipelines that run on Cromwell and these sorts of things. Finally, just going to talk a little bit about where we think of the next frontier here for this space. In terms of what we're doing with our company. Our company is called Beaker. It is early days still for us, but we're sort of looking at these pipeline engines, and we think there is a sort of next step here to help people in this field. Some of the problems we've identified is that in industry or even academia, data can be everywhere. Different groups can use different data storage solutions, different cloud buckets, or some people store things on the cluster, some people store things in SharePoint, etc. So we think there is an opportunity to sort of try to consolidate that for groups of people. In the same way, we also think that pipelines can be sort of a collaboration point for wet lab scientists. Pipelines are a great way of auditing sort of the work done. Wouldn't it be great also if there was a way for bioinformaticians and other people to be able to set up these pipelines for wet lab scientists and maybe even be able to sort of collaborate on results, have discussions back and forth, share data that is not only over email or what have you, meetings, etc. And we also think that pipelines help abstract away a lot of the DevOps challenges, but we think there's still work to do there. For example, if you want to run a Nextflow on AWS Batch, you're still going to have to go on AWS and set up some things. And it's not always obvious to everyone who doesn't have DevOps experience, like what these different services are and the pros and cons of different ones. And what's a service account and how do I set up the permissions and etc. So I think there's an opportunity there. And finally, pipelines being sort of like this reproducible thing that can be shipped to anyone. They have opportunity. There's an opportunity there to help less technical scientists perform common tasks as well. So today, I would say pipelines are very powerful, very great in sort of the single player use case for the bioinformatician to develop things, to figure out how to host it, to figure out how to go run it, to figure out how to connect it to their data sources. But it still requires a lot of sort of configuration, command line, they're not a great sort of point of collaboration for wet lab scientists, etc. So we are working on a desktop app powered by open source pipeline engines. We're going to start with Nextflow. And our tool is going to, on one end of the spectrum, we're going to have, it's going to integrate with all of your sort of data sources. All of your credentials for those data sources will be local. That's why we are working on a desktop app, so that we can sort of get people to use this without worrying about uploading their cloud credentials to some third party in the cloud. So all this stuff stays with you locally. And then part of what Beaker does is gives wet lab scientists and other scientists the ability to perform common tasks using a GUI. If you've ever used the tool like Genius or have heard of it, very similar. However, the difference is that when a common task is performed, Beaker is actually running this behind the scenes using a pipeline. And Beaker will probably ship with something like Nextflow. So behind the scenes, it will spin up a Nextflow pipeline so that all the operations conducted using the GUI are auditable, but can also be modified or tweaked. Bioinformaticians use it to develop, manage, and share pipelines, and also to sort of make pipelines a central point of collaboration between wet lab scientists and other sorts of people to share results back and forth and leave comments and share data. And where we're really going with this is this desktop app by default will run the pipelines locally. However, you also have, because it's powered by open source pipeline engines, we have the ability to connect this thing to your cluster or in the cloud. One of our big sort of value props for bioinformaticians is no DevOps. Download this thing, use it locally. When you're ready, connect it to your cluster. No DevOps, no SSH, no more of that. Or in the cloud, we will set up AWS Batch for you through this tool, or give you like really, really clear instructions. We will tell you how much money you're spending, all sorts of things like that, so that teams can use it to collaborate on analyses. So that's what we're building, and yeah, hopefully one day we have something a bit more to show you one day soon. And yeah, keep an eye out for maybe Beaker. If you hear about us, check it out. And that is all for my presentation here. So thank you very much. I hope that it was informative. You learned something, and of course, if you have any questions, now's a great time. And feel free also to stay in touch via email if you want to, or if anything comes to mind. Thank you very much.
Thank you so much for your presentation. It was very relevant for some topic, especially for me, for topic of reproducibility, which I have many questions of it. So the first question about the reproducibility, I'm wondering why there's a difference between Mac OS and Linux when we use Conda. Because I already have this issue using a package on GitHub, and it was very frustrating when I see too many different results on a different OS.
Yeah, it's really going to depend, honestly, on the underlying shared libraries. Sometimes, so when a tool is shipped, so when you build software, there's kind of two different things you can do. One, if you're depending on external libraries, one of them is you can say, hey, the operating system needs to have this library installed because I'm going to use it. I'm going to depend on it. And the other thing you can do is you can say, hey, I'm going to compile my software so that the library is actually embedded in my piece of software to make sure that, like, hey, my piece of software actually has the exact same version and whatnot. Tools like Conda, they try to manage those sub-dependencies. They try to say, hey, okay, we are using version 3.10 of Python, and okay, we'll stop there. But then maybe Python has other sub-dependencies that it sort of uses, where maybe those like connections, hey, we need this specific version, isn't as like well defined, or maybe on Linux that specific subversion of the package is actually slightly different code than for the other operating system. So there are like the subtleties go pretty deep, I would say. And in most cases, I think that's probably where you end up with discrepancies. Whereas like with containers, all the libraries are shipped with the container. They're all there, even the sub ones. Where containers do their translation is more just at sort of like that syscall level. And the syscalls are a bit more well-defined in terms of like, okay, they're compatible between running containers on Linux or running containers on Mac OS. So you just end up packaging a lot more stuff in a container, a lot more of those sub dependencies, I would say, that guarantee a bit better reproducibility.
So for your opinion, what's the best way to not to have reproducibility issue? Just to use container and using conda plus container, or what's the best steps to use?
Yeah, definitely containers are the way to go. If you like can invest in them and you know, are willing to put sometimes they could be a bit harder to change or these sorts of things. But I think a lot of pipeline engines also actually help abstract away containers now. So if you have the opportunity to use containers for your steps, definitely recommend that because then, for example, when we're building software nowadays, part of the reason why we use containers is because when I'm building software locally and then I deploy it to, we call it production, like the actual service, we want to make sure that's going to run the exact same way. So that's part of the reason why most people in sort of like software engineering have moved to, you know, using containers through and through. And that's one of the big things they try to solve, actually, for sure.
Okay, so as I understand, just to install other package through the Docker image, right? And not using the conda or apt.
Yep. Or even exactly, or even if you can encapsulate a lot of your step, like if you build in pipeline, if you can encapsulate a lot of your step in a container, that's great as well. The more you can encapsulate in a container, the more you will sort of get that reproducibility for sure.
Nice. I have another question. Yeah, how to manage the conflict of the package versions?
Yeah, great question. And actually, again, containers can really help you here.
Yeah.
You have different versions in different containers, right? Because the container will only have the versions that you require for what the container is trying to achieve. So if you containerize, you know, I don't know, like a FastQC, and you need a specific version of Java, which I don't think you need for FastQC, your container can have that specific version. If you have another tool that requires a different version, that container can have a different version.
Oh no, I mean by, for example, I use a package machine learning and conda, and there is some conflict because there is those two package doesn't work together.
Mm-hmm.
So is there a good way to manage that or resolve that very easily?
I think it really depends on the package manager. I'm actually not super familiar with like Conda or different package managers, but in general, like that's part of what they try to do is manage, and I think it's going to depend on which one, but part of what they try to do is manage those conflicts. And then, yeah, if you can get like deep into containers, or if you can't do containers, VMs, like they should be able to help you manage that, as long as kind of like the machine learning thing is separate from the other thing that uses the other version, if that makes sense. So I don't have like a great answer for you for if you're using package managers, but yeah.
Yeah, that's great. About the company of Baker, how do you manage the security of data if you use the software itself? Because in bioinformatics, the data is very sensitive. We use patients' data. So how do you we could trust the software?
Yeah, great question. And this is actually why we're starting with a desktop app, is because we don't want the sort of storage credentials to go to our service, because we know that security and privacy is a really big deal. So the idea is that this is a desktop app. It runs locally. That means only the app on your computer uses the keys on your computer and accesses the storage directly. And by default, the pipelines run locally, but then you could configure sort of Beaker to run on your cluster, and then only your cluster will have access to that data. Those credentials will stay inside of your network, so they'll never go to our service. If you use our cloud service, then we will have access to your sort of storage credentials, because your pipelines will be running in our cloud, which means at that point you're essentially trusting us to be secure with that. Yeah, that's one of our big sort of value props is we think that a lot of these existing sort of like solutions to run pipelines in the cloud, we think they're like a pretty hard sell and pretty hard for people to adopt and try to use, because there's a lot of hurdles around data security and privacy. So that's why we're sort of taking this angle.
Nice. Didn't know about the desktop
Yeah.
app. Yeah, perfect. I think I just have this question. I don't know if others they have question. Let's check on YouTube. We don't have question either.
I have a related question, because I use Genius a little bit, and I know that people in the lab that they are scared of bioinformatics. That's convenient for them. So is Beaker can really span like more expert users towards more lab users? Like how do you plan it to release it?
Yeah, that's the idea. The idea is you have like sort of like your file browser where we show you like you know, nice reports and charts for common file formats. We have like baked in options for doing like assembly. We have like specific UI for QC, quality control. And then for expert users, like they can do all that through the file browser as well. But then there's also like support for like seeing your pipelines and seeing runs of those pipelines, and like uploading your pipelines and sharing those sort of like setup pipelines with lab users as well, so they can use them. And so and also really what we think we can really help with on the bioinformatics side, expert user side, is really like the DevOps angle. And then, yeah, we think there's just a big opportunity for collaboration. But we will, you know, that's one of the challenges that I feel confident we can overcome, is like making it really usable for lab users and making it really powerful for sort of more expert users.
That's a great idea. Yeah, I like
thank you.
it.
Yeah, thanks. Yeah, it's been really interesting to learn about bioinformatics, like really interesting. There's this very wide field, and I feel like there's a lot of opportunity for sure, but it's like finding the right solution that kind of will capture, you know, do things in like has the right angle to it. So we're pretty excited.
Yeah, like bioinformatics spans many, like if you do something in Excel, you can say you're doing bioinformatics, yes, probably. And then more advanced applications, definitely it's very wide.
Yeah. Yeah, you could probably do bioinformatics in Excel all the way down to like writing R scripts. So yeah, it's really wide.
Perfect. No more question? Oh, I have a question from a YouTube channel. So he said academic research in bioinformatics is a lot about open source and free software. How does Beaker insert itself in academia? Will Beaker be free for academia? What's your target market?
Yeah, great question. So the thinking right now is that Beaker sort of personal use desktop app will be free. And again, all powered by sort of like pipelines and open source pipelines and things like that you can audit and see. So we're hoping that academia can get behind that. And then where we're starting to think a little bit more about like paid tiers is probably industry potentially. If you want to connect to your cluster potentially, or features like we're envisioning features such as if you're using Beaker with sort of the cloud, things like estimating cost or performance metrics or things like that, we think could be especially valuable to maybe teams in industry who are willing to pay a bit more for this. And the idea, of course, is like we want to give as much value as possible ahead of time. And then once people really see the value and they decide, hey, yeah, I really want to take this to the next level and upgrade to the cluster version or the cloud version, then it makes sense. But I think right now the thinking is like probably most of the money for this is in industry. So I think some sort of free tier will be pretty significant for academia and and solo users in industry and stuff like that.
Yeah, I think I understand the question of Jasper. It's because in academia they don't have a lot of funds, so it's a bit very expensive for them to use the software that have a.
Yeah, and the way we sort of think about it is, we want as many people as possible to use it in academia, and then if they transition to industry, then they can bring it with them. And then ideally, like the way we think about it is like most of the money probably comes from industry. So we are definitely like thinking about like there will be some sort of free version for academia, maybe for everyone. And then it's just a matter of like, okay, where exactly do we segment it? So we haven't fully figured that out yet. So I'm weary to say like, oh yeah, it'll be free, absolutely free for academia, but that's top of mind for sure.
Nice.
We want everyone in academia to use it. Right.
That's great. Yeah, he said thank you. Yeah, just to know that Beaker is just start 1 month ago, or it's a very new company.
Yeah, we started sort of doing a lot of market research around October, and we incorporated recently. We have a very, very small but mighty team of 3. So it's early, but we are making really good progress. And I actually think we'll have something pretty interesting to show like in the next couple months. So anyone wants to keep in touch, like I would definitely love to sort of show you what we're up to then.
Yeah. Are you going through the accelerator programs that are existing, or you're going through your own stream?
Yeah, right now we are going through our own stream.
If you can say it, of course.
Yeah. I'm thinking a little bit like how much should I say, but no, probably what we'll do is we'll probably right now we're planning to sort of like do a fundraise and probably try to skip sort of the accelerator step altogether. And the reason for that is just because I was doing Dooly for a long time, so a bit more plugged into like the investor network and sort of like the tech community. We think maybe we can accelerate things a bit faster that way. Right now is the thinking.
Yeah, and some accelerators, they require like they want something back, right? Like at UBC, for example, you are kind of bound to the UBC if you continue. But yeah,
right.
Excellent that you have a portfolio of investors. That's great.
Yeah. I mean, I wouldn't say I have like a Rolodex of like people just waiting to give money, but not yet.
Oh, step by step, right?
Exactly.
Perfect. I don't know if there is more question. We will take one more. No on YouTube. Perfect. So we will end this presentation and talk. Thank you so much for your presentation, Justin. And thank you for being here at the second meetup of MonBUG. We'll be in touch for the next month.
Awesome.
And have a nice weekend.
Yeah, thank you. Thanks for having me. It was actually really fun. And yeah, I hope it was informative. And if anyone wants to keep in touch, Justin at beaker.bio. Yeah, would love to keep in touch and learn about everything you all do.
Perfect. Thank you so much.
Thank
Okay,
you.
Thank you. Okay, thanks.
Bye.
Thanks.